Dear students, hope you all are doing well. Welcome to another very exciting session of the course Mechanical Characterization and Modeling of Tissues. So far we have learned quite a bit about the different experimental and computational modeling techniques with the soft tissues. Now we are going to switch gears and learn a little bit about the characterization. Characterization meaning like how can you model this into an equation? How can you model whatever you find from your experiment into an equation, right? And that equation can be used somewhere in India versus somewhere in US, anywhere you can use it. This is typically known as soft tissue characterization. That's one of the key term which we use, and or soft tissue modeling, right? And the way to achieve that is using hyperelastic material models. I might have briefed about this in the very beginning, because majority of the soft tissues have a response which is highly nonlinear. So the stress strain profile is never a straight line, right? So these hyperelastic models allows you to basically model that nonlinearity and kind of factor that into a highly fidelic equation. So let's get started. Let's learn about some of the key equations, how we can implement that nonlinearity and have some nice models and equations, right? So let's get started. Okay. So the first type of hyperelastic material models which have been very popular in the like in academia and market, which have been historically used. Many of these are built back in 1940s, 1950s. Like for example, you would hear about the Fung model, you would hear about a Muni-Rivlins model which has come around 1950s or 60s, not specifically the dates which I remember. But then you have the Veronda Westman model, you have the Yo model. These are very commonly used nonlinear material models. So what are these? What are the basic fundamentals of these models? What is the key foundation? So in order to understand that, we have to define a few things. So the first definition here is the material strain energy function, or it is sometimes known as the material strain energy density function, right? So this is almost used equivalently. Material strain energy function or density function is the same thing, right? So what is this function? This is a function given by the symbol psi. It looks like one of those, like psi threshold kind of symbol. So that's a psi. Psi basically has is a function of three of the invariants of a particular matrix. So if you all have taken ever a course in matrix geometry or have looked at matrix algebra, you would know what I'm talking about. It's a matrix which has a bunch of numbers which are to be operated, and this describes a certain form of matrix or tensor, right? So this matrix is known as the left Cauchy green energy tensor. Basically, what is a tensor? Tensor is something which doesn't change its definition when you convert this from one place to another, or there is a deformation, or there is a rotation. These kind of activities do not change the value or the meaning of a tensor. Tensor mathematics is something which you commonly understand if you have spent some time in the area of continuum mechanics. This is a branch in which we are not going to get into the equations in depth or delve into that. We are mostly focused on the applications, but I will be explaining some of the brief backgrounds into what we are looking at here, right? So this tensor mathematics came from the continuum mechanics, where you're basically looking at when a particular volume is deformed and it is translated as well as it is rotated in the space, which is typically what happens to a soft tissue, right? So what kind of mathematics do you use? You use a tensor mathematics which stays the same whenever you do these kind of operations, right? So one of those tensors, tensor is a very wide term like a matrix. One of those tensors is known as the left Cauchy green energy tensor. So what happened to the right? So there is a right Cauchy green energy tensor as well, right? So this is a Cauchy green energy tensor. This is Cauchy is some person like or scientist like who has basically come up with this name Cauchy green. I think it's Cauchy and Green, maybe different people like who have come together with this tensor. So out of this tensor, basically the left part is of use for soft tissue mechanics and the right is used for some other aspects which I'm just going to skip over. But this left Cauchy Green energy tensor has certain parts in which are known as invariants. Invariants meaning these components in that matrix or the tensor is not going to change irrespective of whether this matrix goes through certain deformations or rotations or translations, right? So if x goes to x1 or y is converted with a rotation matrix, these kind of things do not change this invariance, right? You can read about this invariance and tensors like if you're interested, right? But that's not the point here. I wanted to just kind of mention about these definitions just per se, right? So coming back to this invariants are further functions of certain constants or variables, right? In this particular case, like psi, which is a strain energy, material strain energy function, which is given as a function of invariance I1, I2, I3 of the left Cauchy Green energy tensor, which are further functions of lambda i's. So what are these lambdas? Lambdas are typically known as stretches. From a mathematical standpoint, we have explained what stress, what strain is, what displacement is, what force is. So stretch is nothing but strain plus 1. Strain is the change in length by the original length. That addition with the numerical number 1 is given as the stretch, which is given by the symbol lambda, right? So let's take a look at the figure on the left side. Here we are looking at an isotropic system. What is an isotropic system? Isotropic means, and we have worked with quite a bit of isotropic materials, it means whether I pull this material from the x-axis, along the y-axis or along the z-axis, it's going to give me the same results. That means the material property doesn't change when we go from one axis to another. It's uniform across the system, across the model, right? That is what an isotropic system means. So assuming that on the figure on the left side, this is an isotropic block, which regardless of whether we stretch it this direction or that direction or this direction, it's going to behave the same, right? So we consider this three directions, and we should always have a convention system. This is a system where you have the origin, this entire block is placed hinged at the origin, and you have x1, x2, x3, which are essentially your x, y, and z directions, right? So if I apply a stretch lambda along the x1 direction, which is almost the x direction, here is the same, just the definitions are different, right? We can write it as x1 or x, it doesn't matter. Here just assume it's x1, x2, and x3, right? Let's forget about x, y, z here, right? So if we stretch along this direction, what is the response of this material? That is what we are trying to establish through this set of equations which we are going to look at, right? So let's take a look. So here what we have is we have the strain energy density function, which is psi, material invariance I, lambda is the principal stretches, I1 is given by summation sigma I1 through 3, 1 from 1 to 3 lambda I square. So I1 is basically lambda 1 square plus lambda 2 square plus lambda 3 square, right? It's just a mathematical function, it's a summation function. I2 is given by sigma of lambda I lambda j square, lambda I square lambda j square, right? So what is this? This is basically reads as I2 is equal to lambda 1 lambda 2 whole square plus lambda 2 lambda 3 whole square plus lambda 1 lambda 3 whole square. This is what the I2 is, right? Next is I3, which is, this is a product function. So it is given by product of I1 to I3 lambda I square. This is typically I1, I3 is equal to lambda 1 lambda 2 lambda 3 whole square, product of all the three, or lambda 1 square lambda 2 square lambda 3 square, it's the same thing, right? So this is what I1, I2 and I3 are, right? Now comes, this is just the understanding of it, hyperelastic strain energy functions. Let's take a look on the right side in the middle. So the first strain energy function here is psi Moneyi-Rivlin, which is given by some variables or some constants here. Specifically, mu1 is a parameter, we call it as a parameter, not a constant or a variable. Mu2 is also a parameter. These are the two parameter model, Moneyi-Rivlin. Everything else is a function of I1 and I2, which are further functions of lambdas, right, like we have just explained. So Moneyi-Rivlin equation is given like this. What is this equation exactly? So just think about an equation of a line. It's y equal to mx plus c, right, where m and c are parameters, right. So it's y is equal to mx plus c. If you have a polynomial equation, it could be y is equal to ax square plus bx plus c, something like that, where you have a, b, c as the parameters, right. It's very similar to a polynomial equation. These are some equations which have been derived based on a lot of experiments. These have historically come through experiments, right. And Moneyi-Rivlin are most likely two people, right. Like I definitely know Muni is a person, but Moneyi-Rivlin are kind of the people who have come together through their research to come up with this model, right. So psi Moneyi-Rivlin is a very well-known model, well-known hyperelastic isotropic model in literature, which you can use to basically simulate or approximate a stress strain response which you get from a certain experiment with a soft tissue or any soft material. Makes sense, right? The next thing is Veronda-Westman. Veronda-Westman is another group which has come up with its own equation. They have a little bit more complex. It's an exponential equation, so you need to apply log and anti-log to solve these kind of equations, right? Here the parameters are C1, C2 and C3. Everything else is C1 times e raised to power C2 times I1 minus 3, where I is a variable, right? It's a function of lambda, right? And whole minus C1 C2 by 2, then you have I2 minus 3, where I2 is again a variable, right? It's a function of lambda, which is clearly explained in the I1, I2 and I3 definition in between this slide, right? Next is a Humphrey model, which is again an exponential model. It's a little bit toned down version of the Veronda-Westman model. If you just take a look, it's as if like the C1 C2 thing, the second part of the model Veronda-Westman was just removed. So why did Humphrey come up with this random model, right? These are some adaptations which people have come up through experiments over the time. These are not necessarily in order. This is not the chronological order in which things have evolved. There is a certain order which you can read about it. I'll direct you to one or two publications where this order is clearly mentioned, which one has evolved at which era and which times, like, and that is typically how these models have usually become much more elongated, right. So I'm assuming Humphrey was an initial model. Veronda-Westman came up with a much more complex and much more accurate model to simulate the soft tissue response, stress strain response much more accurately. Let's say I'm just throwing some numbers here. Humphrey was, let's say, 85% okay, accurate. Then Veronda-Westman was probably 89% or 91% accurate. These are some numbers I'm just throwing like randomly, but that's typically how things have evolved, right? Then we are looking at another model which is known as a Yeo model. So if you look at the Yeo model, this is a summation of I to I1 varying from 1 to 3, Ci I1 minus 3 raised to power I. So this is another model which is I would call it as a cubical model, right? So these kind of models, and there are furthermore models like Fung model. There are like there is a another one like which is a advanced version of Moneyi-Rivlin. There are 4 or 5 more models which are widely popular. Like Ogden model is something which is very popular. These are the standard hyperelastic isotropic functions which have been developed over time. And one of the groups which has been really responsible for this is there's a group by a professor known as Holzapfel. I think he's from somewhere in Sweden, I believe. I may be wrong, somewhere in that part of Europe, where they have run a lot of experiments on animal skins, animal tissues, over the past 60 or 70 years, and they have come up with all these models trying to properly or accurately simulate the stress strain response. This is how historically things have come over, right? So can we use these models directly with the psi function and the parameters? We cannot. We have to have a better version of this model, right, which is usable with whatever data which you get from an experiment. So what do we get out of an experiment? What we get out of an experiment is the stress versus strain. We initially get the displacement versus force, or force versus displacement. We convert that to stress versus strain, stress being on the y axis, strain on the x axis. So this set of data we want to convert in, we want to have something similar in the equation so that we can fit something to that data, right, fit a curve to that data, but that doesn't seem to be the case just yet. Okay, so the next step is we go for a stress strain relationship. So the way the stress strain relationship is obtained is if you partially differentiate, these are partial differential equations of the psi function, which is the strain energy function, with respect to lambda. So sigma I, which is I referring to all the three directions, the x1, x2 and x3, these are the three i's, by the way. So sigma I is given by Jacobian inverse. Jacobian is another term which is widely used as a term for incompressibility of a material. I'm not going to get into the detail of these because this is from a standard mechanics of material kind of language, right? But these are not important if you're trying to use a material model and basically simulate some stress strain response, right? I would just give you some foundation and focus on the application, that how can you use this very quickly, all this information, rather than delving into the derivations and history and all those aspects of like these models, right? So through the stress strain relationship, what is achieved is you will basically get all these equations which you can see here in the middle on the right, which are hyperelastic strain energy functions under that headline. All these equations convert to the equations below them, which are the hyperelastic stress strain relationships, where you are getting stress Moony-Rivlin given by sigma Moony-Rivlin as equals to twice of lambda square minus 1 by lambda whole multiplied with C1 plus C2 1 by lambda, right? So this is something which you can operate with or work with. You have a stress term and strain stretch, which is lambda, which is nothing but 1 plus strain, 1 plus epsilon. Epsilon is usually the symbol for strain, right? So now you have an equation which can be fit with a stress strain response set of points which you get from your experiments, right? Similarly, Veronda-Westman, very similar equation you have got. So this is achieved not only through the partial differential equations, but also by applying a uniaxial test condition. Majority of the material models, hyperelastic material models, have been focused on isotropic, which is a simplified version. Most of the tissues are not isotropic, by the way, right? They're focused on isotropic, as well as they're focused on the uniaxial test, which is when you are trying to just pull the tissue along one direction. They are not focused on biaxial or multiaxial tests, which are typically the test conditions or the boundary conditions which a soft tissue would face. Like for example, skin on my arm, they are under a state of biaxial strain, biaxial stress, right? It is never pulled under uniaxial, because if it is under uniaxial, then I'll have wrinkling on the other orthogonal plane, right? So typical boundary conditions which we see in a day-to-day life are all usually biaxial or multi-axial loadings, but majority of the materials have still been like models have been developed given the uniaxial test, which is a very common thing with the UTM. It's a universal testing machine. Sometimes it is also known as a uniaxial mechanical testing device, right? Just because UTM has been a device which is very popular with mechanical testing or characterization of it, of soft tissues, that's why the uniaxial test is something very popularly well known, and all the material models have been developed on the theory of uniaxial test. Okay, hopefully this part is clear. The next part is what happens in case of a uniaxial test. When you have the sigma I in the stress strain relationship, it is supposedly sigma 1 is equal to Jacobian inverse of lambda 1 dou, this is known as a partial differential equation, dou psi by dou lambda 1, right? This is sigma 1. Then you have sigma 2, which is Jacobian inverse lambda 2 dou psi by dou lambda 2. Sigma 3 is Jacobian inverse lambda 3 dou psi of dou lambda 3 given by I 1 to 3, right, separately. But in a uniaxial test, sigma 2 and sigma 3 goes to 0. That is the condition. So you are just left with sigma 1, which is equal to lambda 1 dou psi by dou lambda 1, right. After applying all this, these are the final equations which you get at the bottom right, right. So this is not only a stress strain relationship, this is also applied uniaxial test conditions, meaning that the equations will only be applicable when you have tested a soft tissue or a soft material, assuming that it is isotropic, means it has no fibers or anything going on, it is just same along all the directions, and assuming that it has undergone just a uniaxial test. Okay, so with these two assumptions, these equations stay valid, and these are beautiful equations, widely used. You have them in the ANSYS simulation software, finite element softwares all across, and they are widely used as the industry standard for conveying the test results of soft tissues or soft materials. And that way you have an apple to apple comparison. I perform a test in India and basically come up with this hyperelastic stress strain relationship, and when I publish this as a part of a literature, somebody pulls up this literature, conducts a similar test in US, they have a similar standard to compare it with, right. Otherwise I may have a different test condition, they may have a different test condition, I may have a different device, they have a different device. So this is to standardize all the practices and make sure that, just like modulus of elasticity or Poisson's ratio, which are basic material properties or standards for any isotropic normal material which is linear, this is for isotropic non-linear, one step above where you have hyperelastic modulus. So hopefully this theory or the background is very clear to all where we are headed, right. So our journey in the hyperelastic modeling starts from this isotropic hyperelastic models. Now we are going to step up from here one at a time and delve more into what a tissue should actually look like, and are we able to simulate or model the properties of a tissue very accurately. That's our problem statement coming forward in the upcoming slides. So let's keep going. So the next one is, it's known as a transversely isotropic model. So what does that mean? Transversely isotropic model typically came from the testing of brain tissues. So a lot of animal brain tissues which behave not in a very isotropic manner but have a transversely isotropic nature. What does that mean? So that means along the same plane, if I pull this tissue this side and that side, it's going to behave similarly. But if I pull this tissue from away from the plane, vertical to the plane, it's going to behave differently. So planar isotropy is there, but once you go orthogonal, non-planar, then you have non-isotropic model. That is known as transversely isotropic model. So if I cut the brain into like a like slices of bread, like let's say 10 slices, in each of the slices is the same property irrespective of how I place the specimen in a UTM. If I place it like this or that, it's going to behave similarly. But if I take the second versus the seventh slice, it's going to have a different property. So from one slice to another, the property is different. So that is what is known as transversely isotropic model, right. Okay, so let's get into the equations and problems of it. So let's look at the figure on the left. You are basically looking at the same figure which we looked at in the last slide, which was a much more simpler because we did not have the fibers. Now we have the fibers, right. So majority of the soft tissues, as we know, have fibers. So this transversely isotropic model assumes that in a soft material or a soft tissue there are fibers. However, the overall property of the material when you pull it along a certain direction depends on the contribution of the matrix and the contribution of the fibers. It's just like a definition of a composite material. In a composite material, typically what happens is you have a matrix, you have a set of fibers, or they are sometimes known as reinforcements. So when you pull the entire material, it's going to give very superior properties of the fibers, which are pretty scanty in numbers or volume fraction. They are just placed around. So let's say carbon fibers within a softer matrix. Matrix is very soft, but the fibers are giving all the reinforcement, height, fracture toughness, high strength, high material hardness, and things like that, right? And these are widely used across the industry. I had explained earlier during the initial definition of the soft tissue that we are going to look at soft tissue mechanically as if it's a soft composite, meaning it has soft fibers within a much more softer matrix, right? So we are slowly going towards the definition and trying to make our hyperelastic model better through the understanding of the different models which have been developed to date. Okay, so in this model, what is new from the previous one? In the previous one we did not have fibers, and in this model we have fibers, but we are not looking at how the fibers are interacting with the matrix, which is a very important thing. We are not looking at that here. All we are saying is, I think the fibers have some contribution and the matrix has some contribution. I am going to add that overall contribution and get the overall property. That's all. Where are the fibers located, how much, what angle, these kind of things are not known. We just know there are fibers inside, right? Everything else inside the system is a black box. So this is known as a transversely isotropic model. So the way you define this model from an equation standpoint is by dividing the psi, which is the material strain energy function, into the psi matrix plus psi fiber, clearly meaning that there is a contribution from the matrix, contribution from the fibers, right? So in this, another interesting part is each of this matrix and fiber here, these contributions are considered to be individually different isotropic hyperelastic models. So if you remember, our isotropic hyperelastic models are like Beronda-Westman, Mooney-Rivlin, Fung, Yeo. So we are now considering matrix to be a separate isotropic hyperelastic model, fibers to be a separate isotropic elastic model, hyperelastic model. We are adding the contributions of the both, right? So we have just distributed the psi function into two parts. It's using the same theory of the isotropic hyperelastic model with a little bit advancement or modified version. Now we are looking at the contributions, that it's not an isotropic material, it's soft tissue or a soft material, it has fibers and matrix both. But in what quantity, what is the ratio, what angles, these kind of things we do not know. Please take a note, right? So next comes the stress strain relationship, which is a set of complex equations. I'm mostly going to skip over the derivations and the complex equations, but just FYI, like like what these are, let's take a very quick look. So the stress strain relationship is given by a range of stress strain derivations which are given on the right side. Before we look into the derivations, some of the definitions are important of the terms. The first one is B with block brackets are known as this is known as the left Cauchy-Green tensor, which I was just talking about. Psi is usually a function of that. I is known as an identity matrix. Dev F is a Dimitrov operator. This is just a term of the continuum mechanics. Trace F is trace of a tensor. All the diagonal elements kind of join together, right? So these are some terms you can look at. This is not very important, right? But just for the sake of discussion, if you're interested to know more, I should give you at least some food for thought, like where this is coming from. So that's the idea. The idea is not to scare you with the equations. So the stress strain derivation goes like this: the deviatoric component of this F which is the function is given by f minus 1/3 of trace of f times, these are all cross and dot products typically of the identity matrix, then this is some derivation, and you have the trace component, deviatoric components. These are kind of joined together in different aspects. You can look at the equation. I'm just going to skip over because not many of you will understand what's the background, but I'm going to direct you to one of the publications in which you will be finding all these answers, and that would work as a reference material if you want to go back and just read about it. You are interested in the equation, where this has come from, how this has evolved, how you get the final solutions. So I'll give you that reference material. Right. So long story short, from this right side stress strain derivation, what you end up getting is the stress strain relationship, which is in the middle, right, which basically comes down to this equation, which is stress is equal to 1 by Jacobian of deviatoric component. Deviatoric is just a component of a matrix, right, which is the matrix is formed like this. It's 2 times dou psi partial differential equation, differential of the matrix by dou I1, right, times B, which is the Cauchy-Green left Cauchy-Green tensor, plus dou psi fiber by dou lambda n cross n, n dash cross n. This is a cross product of two, like directional matrix, which will give the third direction. Usually this is a vector and cross products. This whole thing plus P times, it's a pressure term, I. This is not exactly that pressure which we are applying in computational model. This is a different definition of pressure, right? So at the end of the day, what you end up getting is, if you apply the uniaxial test condition where sigma 2 and sigma 3 goes to 0, then you get this equation, which is sigma 1 is equal to 2 times dou psi matrix by dou I1 times lambda square minus 1 by lambda plus dou psi fiber by dou lambda lambda, right? Does this mean or have any value for me? Probably not, right? But what does have a value for me is the equation in the box here at the very bottom. This equation states like this, and this is derived from what equations? Let's just compare C1 E C2, right, which is this equation. So we are looking at the Humphrey model here. So isotropic hyperelastic model, Humphrey was used to define the matrix and define the fibers separately. Just comparing that, here you have the I1 term, it's the same as the lambda square term, whatever you're seeing here, right? So this model was used, lambda f minus 1, that one whole square, whatever. So this is the final uniaxial test equation where sigma transversely isotropic, whichever way you want to name it, it's at the end it's a sigma or the stress is equal to 2 times lambda square minus 1 by lambda C1 C2, first and the second parameters, E times, E is this exponential term, right? You can apply a log to it and it will come back to its form, right? C1 I1 minus 3, the whole plus 2 times lambda, lambda minus 1, C3 C4, these are the two third and fourth parameters, exponential of C3 lambda minus 1 whole square. This is all in the exponential, right? So just to remember, what was the stretch? Stretch is the overall lambda which I am applying to the system, as a whole, not to the fibers, not to the matrix, to the whole material. What is going on out of that to the matrix and to the fibers is nothing of our concern, right? This is the overall stretch due to the virtue of the displacement which are caused in a UTM machine, for example. That is the number which we are looking at. And what is the stretch? This is strain plus 1, right? So this equation, very complex looking equation, just boils down to a very simple equation. It's an equation of stress versus strain, where lambda is strain plus 1 and you have a bunch of parameters which are C1, C2, C3, C4. So if we can curve fit a set of data points which we have got from an experiment with this equation and find out the values of C1, C2, C3, C4, we should be able to get a right curve or a right model or a right equation for this particular stress strain response. That's the goal, right? That was the same goal for isotropic model, that is the same goal for transversely isotropic model. The only difference is we have now looked at or acknowledged that there are fibers and matrix both, but we have not still looked deeper into how much of those contributions are there, right? So this was historically found out to be a little bit better model, not only owing to the range of new terms which are there, like new parameters, like instead of 2 parameters now you have 4 parameters, which is good. Like you have a much more accurate model to simulate a response, but this still wasn't the most accurate, but it was considered to be much more accurate than the isotropic hyperelastic model, which had the very straightforward and blunt assumptions that this is a completely isotropic system and it is going to behave the same in all the directions. So that assumption was basically not considered, and this was considering both the fibers and matrix contributions as a whole. So this was found to be a better model for the brain tissues and got fairly popular with other tissues too. So this is how the transversely isotropic model has evolved over time. Hopefully this theory is clear. Okay, let's go further. Next comes to the we are calling this as a novel anisotropic soft composite model. So this is basically a model I and my lab has created. Okay, so this is part of the published literature. I'll direct you to that. So we can sometime call it as a model which is Chanda et al., like which is my model, like where we have looked at all the aspects of how a soft tissue definition should be, right? And this is also part of the reference book which I've recommended for this particular course, right? Okay, so let's delve into this model. How is this model different and how is this useful, right? So far we have learnt about hyperelastic isotropic model, we have learnt about hyperelastic transversely isotropic model, which just acknowledges that there are fibers and matrix. Now we have gone one step and further steps up, where we are not only acknowledging that there are fibers and matrix, we want to clearly define how much fibers, how much matrix, what is the angle of that fiber, how are these fibers and matrix interacting. That means when you have a overall stretch, how is this stretch getting converted to the fiber stretch, matrix stretch. These all details we wanted to look at, right? That is the only way we can totally or rationally look at a soft tissue by its definition, which is a soft composite. So we have to consider all the aspects of the soft composite. Otherwise every tissue will look very similar. There is no difference between skin or brain or heart tissue. That is not true, right? So in order to properly have a characterization for each of these tissues, what do these tissues differ in? They differ in the material properties, they differ in matrix and fibers, they have different constitutions, and also properties of the fibers and the matrix, or also how the fibers are distributed, whether they are in 2 or 3 layers or a single layer, and the layers are making 90 degrees or 30 degrees with each other, all the fibers are situated in a certain angle. All these things are very, very important, right, to understand a soft tissue completely. That is one of the key goals of this course. You want to completely characterize a soft tissue and find out all the methods to do that, right? So let's take a very quick look into this model, how this is different and what is new, right? So let's take a look on the left side. We are looking at that same block with fibers, but now the new thing which has been introduced is we look at an angle theta. What is this angle theta? So let's say you are trying to apply a uniaxial tension to this entire block by stretching it by lambda, right? So whenever you let's assume in an original soft tissue where you have fibers within a matrix. So whenever I stretch this entire model, it cannot be that the fibers and matrix are stretched in the same way. They have different properties, right? So the fibers will definitely get stretched in a different way, and due to that difference in stretching of the fibers and the matrix, you will see the fibers rotate by a certain angle from their initial path. So let's say the initial direction of the fibers were towards the direction of the loading. Now when you have applied the loading, it moves by, let's say, 25 degrees. What is this effect? This is the interaction effect between the fibers and the matrix. So this is number one what we wanted to establish. Can we define the interaction between the fibers and the matrix? And the way to do that is define that if I apply a stretch of, let's say for the sake, like throw some numbers, if I apply a stretch of 5 units, the angle is going to change by 2 degrees. If I apply a stretch of 10 units, maybe the angle is going to change by 7 degrees, right? So that's the response I'm trying to track when I define this property, right? So this is what is written here, block. So the number one thing which I am assuming here is I am trying to define an interaction between the fiber and the matrix when you apply a overall stress strain response, right? Fibers rotate by an angle theta due to matrix stretching, which establishes the interactions, right? So this is known as an anisotropic soft composite model, which we are claiming, right? So the definition of the equations become much more complex when you move into such a model where you are trying to define an interaction. That's one of the key reasons nobody has tried that so far, like to look at the anisotropy model, because that's very accurate but very complex to define. So here the number one step is to define the soft composite strain energy function. We are calling now the tissue as a soft composite as per the definition which we have basically discussed in the first class, right? So defining soft composite strain energy functions for all fibers in the direction of A naught. A naught is basically the initial direction of the fibers. It could be in the direction of the loading axis, or it could be by virtue of how the fibers are located in some other axis, right? Whatever it is, due to that initial A naught direction of fiber location, what is going on into the system, that is what we are trying to establish through a new strain energy function, which is given as a function of C, which is the Cauchy-Green strain energy function, as well as A naught, which is the initial direction of the fibers. So these are the two functional components which are important. That leads us to the psi, which is the strain energy function, becoming a much more complex function of invariants I1, I2, I3, I4 and I5, becomes much more complex. But what is the gain out of this complexity? We are really trying to establish, can we understand the contributions of the fibers and contributions of the matrix? That's the only way we can properly have the interactions and everything modeled to define a material property of a soft tissue properly. So let's say for example, I'm just taking an example with this mobile phone. This is a soft tissue block. I'm pulling it. There is some material response, some stress strain response. What is happening inside is a black box. I don't know it. What we are trying to understand is what is happening inside, right? So let's keep going. So here, like in the transversely isotropic model, we are now assuming the fibers and matrix to have a different isotropic material property by itself. So fibers considered to be a different isotropic material, matrix considered to be a different isotropic material. The way they are interacting and put together within a composite, that causes the nonlinearity or the non-isotropic or anisotropic response, right? So for example, let's say in a glass of liquid, glass of water, I put some like medicine or something. It's an anisotropic medium, right? Somewhere the medicine is more, somewhere the medicine is less, unless I stir it really well, right? That's a very similar system right here. So inside this system, how these things are functioning, that is what we are trying to understand stepwise. So but the medicine has its own single property, which is an isotropic property. The liquid has its own property, which is an isotropic property. Very similar. The fiber has its own isotropic property, The matrix has its own isotropic property. We are bringing them together. We consider them separately as two different Neo-Hookean type isotropic models to start with, very similar to the definition of the transversely isotropic models. Next is we define the fiber matrix interaction. The way this is defined is through some matrix transformations, through some rotations, transformations, which are, if you are interested to read about it, you can look at it in the publication which I'll refer, you know. So anyways, we start with this A naught is equal to initial fiber direction, which is given by E1, which is usually a unit vector matrix. 1 0 0 means there is just a 1 unit stretch along the x axis, and 0 0 no stretch along the other axis, right, from a matrix or vector description. T is transpose here. Transpose is like the whole thing written like this is to be written like this. That's a transpose. If a deformation f, these are all vectorial terms which we are using. F doesn't mean a force. These are all vectors we are talking about. If a deformation vector f is applied, the deformed fiber direction becomes f a naught, vectorial multiplication, right. F a naught is then rotated back to E1 to look at what really happened there while this got rotated, which is given by f star is equal to R2 R1 f. These are all rotational matrix, right. There are some other definitions like what I4 and I5 are. I4 is given by A naught dot product C dot product A naught, right. I5 is given by A naught dot C square A naught. C square is not necessarily, C is a matrix, right, so it's C times C. So matrix multiplication doesn't give a square value per se, right. If you look into it, it gives a very different value. Lambda f is the fiber stretch. Lambda is the overall stretch to the material. Lambda f is just the fiber stretch, right. I1m is basically the invariant along the direction of the matrix. I1 invariant, this is given by the trace of Cm, which is the Cauchy green energy tensor distributed into two matrices. One is for matrix and one is for fibers. So Cm is the matrix component of that. Two matrices are different. One is a fiber matrix that's used in a composite, and one is an equation matrix, right. So I'm talking about that, right. I1f is the trace of the Cauchy green tensor, which is the fiber part of that. E1 dot E2 is equal to 0. These are some standard math. E3 is equal to E1 cross E2, cross product and dot product, straightforward, right. F star is the new deformation gradient tensor, right. So there are some equations and tensors which we look at. We slowly get into this. Next is we want to define this fiber matrix interaction. So this is done by mathematically multiplicatively decomposing f star, which is the deformation applied, into ff star, which is the deformation or the change applied in the fiber direction, and fs star, which is a subsequent shear deformation due to this interaction on the matrix, right. From an equational standpoint, f star is given by fs star ff star, multiplication of that, which is given by this matrix, which is lambda f, f12 star, f13 star 0, f22 star, f23 star 0 0, f33 star, right. So then if you are looking at ff star, that is a diagonal of on the right side, lambda f half, that's a negative half, means root, square root, and then you have lambda f negative half, which is again square root, right. fs star is given by f star inverse of ff star, which is just a different ways of looking at it, like it's just taking one thing and another, kind of unitary method for the matrix, right. So anyways, like long story short, the next part is into the system, whatever we are trying to develop, where the interactions are there, we would like to introduce strain energy stored in the whole composite due to the uniaxial deformation ff star. At the end of the day, the entire material is still going into the UTM, which is a uniaxial deformation, but that uniaxial deformation is causing deformation on the matrix and deformation on the fibers, right. So by the rule of mixture, which is a very common technique or method in composites equations. This is given as this psi f, which is the fiber component of the strain energy density function, is given by psi f due to the matrix and psi f due to the fibers. What is this exactly? So the overall energy stored in the fibers is due to the contribution of the matrix based energy on the fibers and the fiber based energy on the fibers, right? That's just the interaction model. Long story short, what this comes down to, this is converting into something where you have a term which is known as nu m, which is given by the matrix contribution or the matrix volume fraction. So this equation boils down to nu m C1, C1 is a parameter, I1 FF star minus 3 plus nu f C2 I1 FF star minus 3, right. So nu f is fiber contribution nu f plus nu m is equal to 1, okay. So nu m is 1 minus nu f and so forth, right. So these are all ratio contributions, nu m plus nu f, these are known as fiber volume and matrix volume contributions or volume fractions. These are standard terminologies, right, for any composite text or any applied mechanics system. But I'm going to take you to the conclusion. This is just for those who are interested in knowing some of the details and the foundation. I think that's important because so far we have talked, from an overview standpoint so that everybody understands. But this is where we delve a little bit into the equation part of it, because characterization has a lot to do with the equations. So now this equation comes into the picture using the rule of mixture, and then I1 FF star is further defined where we have this as lambda f square plus 2 by lambda f, which is given by I4 plus 2 I4 square root, and there are a bunch of equations on the right side. What this boils down to next is the shear deformation application, which is Fs star. So first we apply the Ff star, which is one component of the F star overall deformation, and then we apply the shear deformation. Shear deformation is just 1 minus the overall deformation, right. So C3 I1 minus I1 Ff star. These are equations I am not like specifically going to explain much, because these are standard equations and you can look at it, like I am going to give you a reference material to look at it, right. So ideally the strain energy function becomes a sum of the strain energy of two steps, which is the Ff star and the Fs star, right, and it boils down to this large equation which is on the box on the very top, which is given as psi is equal to psi f plus psi s, which is the energy density due to the function of the due to the fiber contribution, and psi s, which is due to the shear deformation component, right, which is finally given as nu m C1 I1 FF star minus 3 plus nu f C2 I1 FF star minus 3 C3 I1 minus I1 FF star. This is the shear component. If you apply the uniaxial test condition, the applied stretch becomes equal to the fiber stretch, okay. So the I1 minus I1 FF star goes to 0. So from a Neo-Hookean perspective, where we have started with both the matrix and fibers as separate Neo-Hookean materials, the material property goes down to this. It is nu m C1 plus nu f C2 whole times lambda square plus 2 by lambda minus 3. Very simple equation, but this is not usable just yet. You apply the stress strain relationship along with it, which is the standard equation which I have explained for also the isotropic and the transversely isotropic model. With the uniaxial test and the stress strain relationship, the final equation is very simple. It comes down to what you have in the bottom. This is known as sigma Neo-Hookean modified. We are just calling it modified because this is considered the isotropic properties of Neo-Hookean for fibers and matrix separately. Sigma is given by 2 times nu m C1 plus nu f C2 whole lambda minus 1 by lambda square. Lambda is known from the experiments. Sigma is known from the experiments. What is nu m and nu f? nu m plus nu f is equal to 1. So if you know one, you can get another. These are some predefined numbers. How do you find the fiber volume fraction? So you usually find it through microscopy. You take a tissue block, you microtome it, along the cross section you look at the fibers by doing some kind of like imaging modality, and you look under a confocal after doing staining and all that. So you look at where the fibers are located, you look at a few slides, take the average of that, based on that you get the fiber volume fraction within the system. That will be the nu f, nu m is 1 minus nu f. So through microscopy you are going to get the nu m and nu f. So all that you have to find out still is C1 and C2. So it's the same stress strain equation where mu f is already known through microscopy, and you need to find C1 and C2. So this is much more accurate version of understanding the soft tissue block. We are going to continue from here and delve a little bit deeper into the soft tissue, what all other model changes or updates we have created to reach to that ultimate step where we can completely define how a soft tissue would look like, right? So stay tuned, we are going to continue with this. Don't get scared of the equations. I'm going to explain this in a way that you can you have some usable values which you can use directly when you get the experimental results. And I'm also going to take an example, explain it through an Excel sheet, how you can apply this hyperelastic model into an actual stress strain property results which you have got from the experiments, right? So we are going to talk about all this, and this is a very important part of nonlinear soft tissue characterization. So just stay tuned and we will see you again shortly. Thank you.